Boldly going where no science show has gone before. The Naked Scientists.
Hello, welcome to this week's Naked Scientists with me, Chris Smith, and also with Helen Scales. Hi, Helen.
Hello.
And with Dave Ansell. Hello, Dave.
Hi, Chris.
Now, in this week's festive Christmas edition of the show, how scientists in Japan have developed a system that can read your mind and see what you're seeing just by looking at your brain activity. Also, a scientific solution to make cheap plonk taste half decent, which could be good at my Christmas table this year. And also how scientists have used the same technology that's used to make unbreakable spectacle frames to make earthquake-proof bridges. And we'll be hearing how they've done it in just a second. Helen.
Thanks, Chris. And this week it's our Christmas special with lots of questions and answers. So we'll be tackling all your science questions as well as doing a bit of practical research to answer an age-old question.
And now, so I'm just going to finish off this champagne and then we're going to have a go on the test and see if it's impaired my ability at all.
Yeah, an excellent idea.
And I wish I had been the one doing that test, but we'll find out later on whether champagne really does make you drunk more quickly. And the lucky one, Mira, got to go along and find out. But we'll be finding out later on in the show what she discovered. Dave.
Cheers, Helen. And in this week's Kitchen Science, I'll be showing you a neat party trick to try out over the turkey at the dinner table on Christmas Day. You can create your own pressure wave. If you want to have a go, all you need is an empty plastic fizzy drinks bottle and a little bit of tape.
Thank you, Dave. And if you've got a question for us, of course, or you just want to say hi, you can get in touch by telephone, text or email. The lines are open now. It's 0845 30 50 007 on the phone. You can text in 07786 20 1960. The email address is chris@thenakedscientist.com.
The Naked Scientist Podcast. Powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
This month, scientists have made an extraordinary breakthrough because they've discovered a way to see what a person is seeing just by reading their brain activity. Now, this is the work of Yoichi Miyawaki, who's a researcher at Kyoto's National Institute of Information and Communication in Japan. He and his colleagues have got a paper in the journal Neuron this month. What they did was to make use of the premise that the retina, which is the part of the eye that turns light into nerve signals that the brain can understand, projects or sends nerve signals to different bits of the brain. And so when the retina receives a signal, so when it sees something, the bit of the brain that it's communicating with becomes more active. And you can see that slight increase in activity if you put people in a brain scanner. So what he and his colleagues did was to put two male volunteers, in a brain scanner, and they showed them small patterns to different parts of their retina, and these patterns were overlapping slightly from one pattern to the next. And so what they did was, in excruciating detail, mapped out the visual area of the brain to see which bits of the retina mapped onto which bits of the brain, and then they were able to show these people patterns, for instance, a plus sign or a cross or even a square, which was a white square on a dark background, for example. And then by decoding what bits of the brain became active, their computer program could work out, therefore, what the person must have been looking at and reproduce the pictures. And in the paper, they have these extraordinary images where you can compare the pictures that their computer generated based on the brain activity and the picture the person actually looked at, and they're almost the same. So this is the first time anyone's actually done it with physically showing an image recreated just in brainwaves.
Would this work with, if you're imagining an image, so if you had a very vivid dream, would that be likely to be triggering the similar sort of neurons, or is this happening very, very early in the processing?
No, this is exactly right, Dave, because the researchers go on and say you don't just have to look at visual information, you could look at any aspect of brain processing with this technique, because you could look at how movements are generated, for example. You could look at how colour is generated. You could look at faces. Faces are decoded in an entirely different part of the brain, in the superior temporal gyrus, which is on the side of the brain adjacent to where your ear is approximately. There's a whole area of the brain just devoted to working out what face you're looking at. So they're saying you could use exactly the same technique they've developed and apply it to all different kinds of processing modalities. But obviously it's early days. This is just a proof of concept, but it shows that computing and scanner technology has come on so much now that you can actually pick apart activity down at the level of almost individual clusters of nerve cells, which is pretty extraordinary.
Well, I'm going to take things down a peg or two from very intricate science to something that we will hopefully all be able to benefit from one day. And since the festive season is upon us, I'm sure that lots of us will be raising a few glasses of wine in celebration. I certainly will be. But this week we have news of a novel way that scientists have found to give a boost to a cheap bottle of Plonk. And a revolting young table wine could be transformed into a nicely refined, well-aged tipple simply by zapping it with electricity. Now, you might expect that it was the French, possibly, or maybe the Australians or the Chileans or one of the, well-known wine-producing nations that might have come up with this new bit of wine trickery, but you'd be quite surprised to find out it was actually the Chinese. This was the brainchild of Xingang Zhen and colleagues from the South China University of Technology in Guangzhou in China. And they're quite a relative newcomer, I must say, to the world of fine winemaking. I don't know about you guys, but I've certainly never tried a Chinese wine.
Never.
I've had Malagasy wine, and I really wouldn't recommend it necessarily. The white's okay, but definitely steer clear of the red. Anyway, Zheng and his teams began experimenting with Chinese Cabernet Sauvignon wine, and what they did essentially was pass it through a tube with 2 titanium electrodes hooked up to an electric field, and they found that the optimum time to expose the wine to this electric field was just 3 minutes. No more, no less. And they don't actually yet know why this is happening. We can't quite explain what is going on with these electric fields and why it's altering the wine's chemistry, but we do know it does seem to work. They gave these wines to a team of wine experts, and they didn't obviously think that they were absolutely amazing wines, but they were certainly better than they should have been. These were 3-month-old wines, which should really be undrinkable.
Were the electrodes actually in the wine, Helen? Therefore, are they electrolysing the wine, a bit like a battery almost, or were they just creating a field around the wine, and therefore that's a bit different, isn't it?
I think what they did was, although I do apologise if I'm wrong on this, I think it was just passing the field through the wine.
I think they had 2 titanium electrodes inside a pipe.
It was inside. Okay, sorry.
And then they put electricity between the two electrodes through the wine. And that
okay,
had the
great.
effect.
Thanks, Dave. Sorry about that. So this they did. So it could be something to do with electrolysis. But what's going on inside the wine, no matter what actually is causing it, is essentially changes in the chemistry. You've got various bitter organic acids in the wine, which is what really are making it taste very badly. They react with the ethanol to create things called esters, and they're fruity, nice flavoured compounds that actually help the wine tastes better. And that's the sort of thing that usually happens, but very slowly as the wine ages. That's why wines only really should be drunk after 6 months. And of course, a really good wine keeps getting better and better for decades and decades.
But Helen, people say, if wine tastes bad, it probably tastes bad for a reason. So should we really be trying to spruce up dodgy wine to make it taste good? Shouldn't we just go and buy decent wine?
I think you're quite right to some extent. I think wine connoisseurs are unlikely to say, hey, this is fantastic. This is, a replacement for all that, the wine-making skill that we've developed for thousands of years. But I could see how maybe for certain cheaper wines, perhaps it would make them a bit nicer, because there are people who, let's face it, don't want to spend more than a couple of quid on a bottle of wine. But I must say, they're trying this out in China, and we'll see whether or not the Chinese wines really will hit the market with this new electro wine treatment. But I would say, if you're feeling a bit impatient this Christmas for a tasty glass of wine, please don't try this at home.
Just red wine, was it, or does it work on white wine too?
I don't think they've tried white yet.
May have to go out the garage later. Now,
it's not because he drinks meths or anything, but because it doesn't make meths taste better, I presume. But no, he means as in you're going to do some experiments, presumably, Dave.
Well, I wouldn't say it. I'm sure it's... Anyway, back onto the subject. Now, slightly more seriously, the destruction produced by earthquakes can be devastating in itself, but often the knock-on effects of this destruction can be even worse. For example, if an earthquake damages a bridge beyond repair, there's not just problems with people on or around the bridge. It also means the emergency services can't get across the bridge to help put out fires on the other side, and generally support people on the other side. In the longer term, of course, a lack of bridge could slow down rebuilding after the disaster and entirely ruin the economy around either side of the bridge. Now, engineers at the University of Nevada are trying to reduce this problem by using modern materials. The cause of much of the problem is that the steel that's used to reinforce the concrete in the bridges, during a large earthquake, this is designed to bend so it absorbs some of the shaky vibration energy. This is quite effective at stopping the whole structure collapsing during the earthquake, but the problem is that this can actually cause a bridge to be damaged beyond repair, and so you can't drive over it.
Yeah, so it's actually all it's doing is stopping the bridge killing people when it falls, but it's not actually preserving the bridge at all.
Yeah, it's sort of a bit like a crumple zone. It survives the earthquake without killing anyone, but you wouldn't want to use a car afterwards.
So what's the solution?
Well, they've been using a kind of material called shape memory metal called nitinol. This is the sort of stuff you sometimes get in glasses frames, so you can sit on your glasses, they're bent, but they'll sort of spring back to the original shape. So the idea is that instead of using the steel reinforcing, you make reinforcing out of this nitinol stuff. It's made out of nickel and titanium. And so that when the bridge shakes a lot, it'll always spring back to its original shape. And because a lot of its strength is to do with its original shape, it might not be as strong as it was to start with, and you might need to do a few kind of superficial repairs, but it's not going to fall down, and you might be able to drive over it carefully immediately after the disaster, and you can recover a lot quicker.
Buildings as well?
They haven't looked into this. They actually, with this, they built a model bridge about sort of 200 feet long, and they shook it really violently. So they've only looked at bridges so far, but I see no reason why you couldn't do it with buildings as well.
Thank you, Dave. Now, also, what we thought would be quite fun to do this year was to ask everyone to take a look back over the previous 12 months to pick out some of the items that have been discovered this year which we thought were the most funny, fun or intriguing. So I'm going to kick off, and this story came out around about February time, and it tickled my fancy because I have an interest in neuroscience and how the brain works, but also I have a bit of an interest in music. And one thing that I was always intrigued by is how people manage to improvise. So if they sit down at a piano, if they're an experienced musician, and they can just tinkle away, and they produce these beautiful sounds which add ambience to a setting. They don't dominate, but at the same time they're interesting to listen to, but they also don't seem to follow the same musical patterns and rules that you associate with a classical piece of music. How is that person doing that, and how are they making it all make sense and sound good at the same time? And that's what was going through the minds of a couple of American neuroscientists, Alan Braun and Charles Lim. They published a paper in PLOS One earlier this year where they put a whole load of jazz pianists into a brain scanner to find out which bits of the brain they used to do improvisation. Now, the way they did it was to set up a protocol that would disentangle the bits of the brain that are active just by playing any kind of music from the bits of the brain that are involved in doing improvisation. So they first of all put them in the scanner, gave them a modified keyboard that they could play in the scanner and have the sound that they would be producing played back to them in headphones. They then asked them, first of all, to play some bits of music from memory, in other words, well-learned pieces of music, and this would disclose the parts of the brain that are involved in remembering music and the parts of the brain involved in actually physically generating the movements to play music. The next thing they did was to say, right, now we want you to start improvising. They rescanned them again and then subtracted the results of the first scan from the second scan, which should leave behind just those brain areas which are associated with the improvisation process. And two very interesting changes emerged. There was a very big reduction in the activity in a part of the brain called the dorsolateral prefrontal cortex. This is the part of the brain right at the front which is concerned with self-censorship. It's on the outside edge at the front of your brain. So if you go into a job interview or you're being asked hard questions in a radio interview, for example, and you know people are hanging on your every word, this is the bit of the brain you'd be activating. It's your watch what I'm saying next centre, if you like. And that was very strongly switched off in these people when they improvised. And at the same time, another bit of the brain called the medial prefrontal cortex, which is in the centre of the brain but at the front, that was very strongly activated. This part of the brain is activated if you tell people to tell a story and put themselves at the centre of it. So tell a story about yourself, where you're the focus of attention. That bit of the brain switches on. And not surprisingly, in these jazz pianists, when they're improvising, they turn off their self-censorship, they activate this region which is involved in spontaneous information about them, making themselves the focus, and that's probably how they channel this uninhibited flow of ideas and energy from the creative bits of their brain. And as one of the scientists said, they often play with their eyes closed in a distinctive personal style that transcends traditional rules of melody and rhythm. And that looks exactly why. Helen?
Do we think, this is fantastic just to think, you know, what's going on inside these musicians' brains, but do we think that there are some people who are just naturally better at that kind of thing? Their brains are wired up the right way, if you like, and that's why they're better at improvising. Do you think that could be the case?
It certainly could, and in fact one of the points they make in their paper is they'd like to now also look at other kinds of artistes, writers, poets, painters even, and see when they show free expression whether there is the same pattern of activation, because this would suggest that it's partly to do with disinhibiting yourself, it's partly getting yourself in the right mindset so the creative juices can start flowing.
Cool. Now, a story from earlier this year, which hopefully will be the start of big things to come, was the news that the small California-based company called SpaceX has managed to build a space rocket and put a satellite into orbit. Now, this might not seem particularly impressive as governments have been doing this for 50 years, but what's new is it's been done by a private company without state support. Now, it's quite a nice story. Now, SpaceX was started by Elon Musk, who's a South African entrepreneur who made hundreds of millions from publishing software and then from PayPal, which you've probably heard of, which you pay things for eBay. Now, PayPal was sold to eBay and he got loads of money and he wanted to do something interesting with it. First, he thought, I know what would be cool, let's start a Mars program. But he actually looked into this and discovered the problem is that launching stuff into space is so expensive that even his hundreds of millions weren't enough to do anything interesting on Mars. So he decided that the solution to this, instead of just going into a corner and going, I'll just play with my money and become a playboy, he decided to do something about this problem. So he built his own space rocket business, basically building space rockets. He's got a production line in California making space rockets. His first 3 launches didn't work very well. The first one exploded on takeoff. The second one, the fuel inside started sloshing about and it fell over.
Hopefully with no one on board.
Yeah, they're all unmanned. And so that one didn't. And the third one, it was really depressing, actually. It didn't quite work because he changed the second stage space rocket engine. And the idea is you push the first stage off and then the second stage ignites, but the first stage carried on going for longer than it should have done. So the first stage and second stage couldn't separate, and so it crashed into the ground. But fourth time lucky, in September he got this space rocket up into space, and this can lift about half a ton into low Earth orbit. But he's not stopping there. Beginning of next year, he's trying to launch the Falcon 9, which should be able to put up to 12.5 tons into low Earth orbit.
Wasn't there a prize associated with doing that?
There's a prize associated with getting a person up to what's called space, which is 100 kilometres, but not into orbit. And there's another one with getting a person into orbit. But he's just basically got a satellite up into orbit, which there aren't any prizes for. But in many ways, I think this is more important because actually getting stuff into orbit cheaply could mean that we can do all sorts of interesting things. We can go out to the Mars, the rest of the world, the rest of the solar system, put up bigger, cheaper telescopes and find out more about the universe.
Yes, because Burt Rutan got the prize for first... it was suborbital, but the first zero-gravity type flight with Spaceship One, wasn't it? Spaceship One? He did that a little while back. So the next big goal is to get someone up into orbit. Helen?
I could tell by the grin on Dave's face that he just wishes he was the guy who was throwing things up into space, and maybe
wants to build the rocket.
Maybe one day he will be. I think that could well happen. Well, I shall finish off the news this week with what I think was the best news from this year, and I don't suppose any of you will be surprised at all to hear that it was the seahorses arriving in the River Thames in London. I just think this was wonderful. That was reported earlier on this year. I think it was Easter this year, that the Zoological Society in London had actually for the previous 18 months been looking at a population of short-snouted seahorses living in the River Thames, and this was the first time really we've seen a permanent population. A few have washed in occasionally. I think there was one seen in 2004, and then not since the 70s, I think. So really these aren't creatures we expect to see in the Thames, and they're now known to be living there, reproducing, living in a nice little population as far west, I think, as Dagenham, so sort of coming up into the river.
Blimey, they've even gone to Dagenham.
I know. I don't know why they chose there.
And my family are from there. It's okay, I can say that.
Of course. Well, they obviously think it's great. It's still a bit salty there because seahorses don't live in fresh water, so there's enough of a tide still coming in there. So I think it's wonderful, and it was the reason we were allowed to announce the story and let everyone know they were there is because now seahorses are protected in the UK under the Wildlife and Countryside Act, so you can't go and collect them, you can't mess around with them, disturb them anyways, just leave them be. And I hope, just be really happy and proud that the Thames is clean enough now for these lovely creatures to live in.
Thank you, Helen. It's The Naked Scientists with Chris, Dave and Helen. It's our Christmas special science phone-in, so any science questions on your mind, the email address for the programme is chris@thenakedscientist.com.
Lifting the lab coat on the world's best science. The Naked Scientists. For more information, look us up online at nakedscientists.com.
Now, we had an email from Ian Curzon who said, "Hi to you all, love your show. Now, my question is, what are your top 5 science facts? Things that will amaze us listeners so that we can brag about them down the pub, etc." I thought that was a really terrific question, so I thought we would ask everybody for their top 5 facts, but also you at home. So what are the scientific facts or figures or statistics which you find most mind-boggling or most amazing? If you've got a science fact that you'd like to share with us, the email address is chris@thenakedscientist.com. Dave, got a question here for you which has come from Alton Vandiver, and he says, can you see satellites with a telescope?
You certainly can see satellites with a telescope. Looking on the web, there's a guy of definitely large satellites. You can get quite good pictures of them. You can see the International Space Station in quite a lot of glory. You can see all the different bits of it with a large telescope. You can actually see it with your naked. You see them with your naked eye. You'll be able to see stars. If you see stars which move across the sky very quickly, don't have a red flashing light. 'Cause those are normally planes. But anything moving across the sky very quickly is normally a satellite.
I saw a couple of guys on the BBC website actually who have got this tracking software that they've written themselves and some amateur telescope gear, and they have got these amazing pictures of the International Space Station, and it really does look like a computer game actually, how good the pictures are. Yeah,
and also you can sometimes see satellites which aren't supposed to be there. One of my housemates has got a friend who was taking photos of the sun, he's an astronomer, and occasionally you see satellites going past the sun, and you can actually see them in some frames of this video, and there are lists of all the satellites which are supposed to be there, and it was one which wasn't supposed to be there. So there's definitely more satellites up there than anyone will admit to.
Also, they fool people because some of them come down into lower orbits and then go back up again, and you get these interesting iridium flares where the iridium network of satellites, which is telecommunication satellites, come down low in order to communicate, and then they go back up higher, park them into higher orbits when they're less in demand, and it means that they're using less fuel in the long run because they're not having to keep accelerating their orbit all the time. Here's an interesting question for you, Helen. A little bit saucy, this one. Mick Holmes says, why does my dog always poo on the path and not on the grass?
I want to know why you asked me that question, actually. I'm not really au fait, don't have a dog myself, and I'm not necessarily any the wiser for why this might be. Could be all sorts of reasons. We were discussing this before the show. Maybe it was something to do with marking his territory, perhaps. We think perhaps poo, as well as wee and lots of other urine and other fluids like that, are good for letting other dogs know where they are and if that's their territory or not. So perhaps they think that a path where other dogs have walked along, left their smells, would be a place to leave their little mark. I was wondering if maybe it thought it was a cat, because I think cats would be more likely to dump... I didn't say the word dump, sorry. This is all getting very silly. To defecate on a path than on grass, because cats like to try, at least, to cover up their mess. So perhaps on a sandy path, that might be better than on the grass. Maybe the grass is spiky and it doesn't like the feeling of it.
That's right. A couple of people on our forum have speculated. This is nakedscientist.com/forum. You can put your comments or thoughts there. Dr. Beaver says, using Occam's razor, the pavement doesn't tickle its bottom when it squats, but perhaps in the same way as the grass. And the person who calls themselves Dent Student says, I guess it's because dogs don't have the same social cues as humans and don't consider it to be antisocial to poo on the path. And then someone points out down there saying, are you saying, Dent Student, that you do poo on the grass?
I'd say it's pretty antisocial to poo on the grass anyway. I hate treading in dog poo. So anyway, I hope when the dog does poo on the path, you do clear it up afterwards. Thank you very much.
I've got a question here for you, Chris, from Ricardo. He's heard that there's some strange liquids or waters that people like SAS and Navy SEALs can use to breathe at very, very breathe instead of air at very great depths underwater. Do you know anything about it?
Yeah, this is called liquid breathing, and it's been experimented on for a little while because also there's some occasions when actually forcing gas into lungs is bad, because if you've got an adult, for example, with respiratory distress syndrome, and this can also affect young babies that are premature, the problem occurs when the lungs have a deficiency of a chemical called surfactant. And because the lungs contain lots of tiny air spaces called alveoli, the linings of those air spaces are kept saturated with water. They're wet. And water makes something called a hydrogen bond. It's a sticky molecule, and one molecule tries to stick onto another. And this would collapse the alveoli down and make them disappear if you didn't have something there to break this water bonding, that would make it less sticky. And this is what these surfactant molecules do. They help it to remain bigger. And so when people have some kind of lung conditions, and this is premature babies don't have this stuff, adults can have certain conditions where they lack this stuff, you don't have any surfactant, and as a result the airspace is trying to collapse, and as a result it becomes very, very hard to inflate the lungs, and so you have to use very high pressures of gas being blown into you in order to keep the lungs inflated, and this can do damage. So scientists have been exploring the possibility of using fluids instead of gas under certain circumstances, and also in deep-sea divers. And some of the fluids that they've been exploring are fluids that don't mix with water, so they're organic chemicals, and perfluorocarbons are the class of chemicals involved, and they've done experiments with chemicals with 6 carbon atoms in a line. That's perfluorohexane. They've also done experiments with 8 carbon atoms linked together called perfluorooctanes. They haven't been done on humans. They've been actually done on sheep, which are a good model for us because they're mammals, they're big mammals, they have lungs quite similar to ours, so they make a good model. And what is special about these chemicals is that you can persuade lots of oxygen to dissolve, and lots of gas, actually, of any kind, to dissolve in this liquid. You then pump the liquid into the lung, and it then passes the oxygen into the blood, picks up the carbon dioxide, and you pump the liquid back out again. And the problem with this is that lungs are made to move gas, not liquid, and so it's very, very difficult to move large amounts of liquid like this. So really the only time it's practical is when you have someone mechanically ventilating you, in other words, moving the liquid in and out for you. One place where it might therefore have a role is in things like intensive care. It might be possible to use it in those settings, in people with damaged lungs, to get lots of extra oxygen in and carbon dioxide out. Another situation where it might be useful is in the context of deep-sea diving, because when you go deep-sea diving, something you're well acquainted with, Helen, there's a risk of the bends. As you go down underwater, the pressure of gas you're having to breathe in is increased from your tank by your regulator to overcome the fact that you're under pressure underwater. So you're now breathing gas which is at much higher pressure and much higher density than gas at the surface, and this forces a lot more nitrogen into the blood, and nitrogen does not dissolve very well at all. It's very, very insoluble in water, unlike oxygen, and as a result, when you take the pressure off of the person again, the extra nitrogen that has dissolved in their tissues can come out as little bubbles, and it forms bubbles in blood vessels and blocks them up, and that's why you get decompression sickness, the bends. If you used a liquid in the lungs instead of gas, the liquid would not succumb to the increased compression of being down deep, and therefore it would not force extra gas into solution in the same way that air mixtures would, and therefore it might in theory be safer if we can overcome the other problems that are associated with it.
Have you seen the film The Abyss? It's one of my favourites as a diver, and they use liquid breathing. I think they put a mouse in a plastic bag, and and that's fine that way. But that would be fun if that happened one day. This is The Naked Scientist with Chris Smith, Helen Scales and Dave Ansell. Now, Christmas and New Year are a time for celebration, as we all know, and for popping open some champagne or sparkling wine. I certainly will be enjoying a tipple, I think, this Christmas. But many people claim that champagne goes straight to their head, getting them more drunk more quickly than non-sparkling wine. We sent Mira to find out if this really is the case, that bubbles really go straight to your head, by exploring the science of champagne.
Fancy cracking open some champagne to welcome in the new year? Well, it may be worth you noting that the bubbles that make this drink go pop when you open it will get you drunk a lot faster than its wine relatives. I'm with Fran Ridout, Clinical Research Manager for the charity Saving Faces at St Bartholomew's Hospital in London. Now, Fran used to be based at the University of Surrey, where she looked into the effects that champagne has on our brains. How did you go about looking into the effect of champagne?
We used a psychometric test battery which measured reaction time, people's ability to attend to a stimulus while doing something else, their vigilance, their ability to do something for a sustained time, and their short-term memory.
Who did you test it on, and how did you go about getting your samples?
We actually did the tests on volunteers, work colleagues. We had 12 people and they had 2 different drinks. One of the drinks was ordinary champagne and the other drink was champagne which we'd whisked all the bubbles away from with an electric blender. We had people drink both drinks on different occasions, a week apart. So one week they would have champagne with bubbles. The next week they would have the champagne without bubbles, which they thought was ordinary wine. They didn't know the purpose of the experiments. Everybody did a baseline test before they'd been drinking. They then drank a measured dose of the champagne or degassed champagne according to their body weight. Then they did the tests again 20 minutes after and 60 minutes after drinking.
And what did you find?
We found that the champagne with bubbles was much more impairing than the champagne without. We found a difference on all the tests between when they did it before they'd drunk anything and afterwards, apart from short-term memory. With the still champagne, the only test that was impaired was a simple test of reaction time.
And you also looked into the actual blood levels of alcohol in the people?
Yes, we also took blood samples after 20 minutes at 5-minute intervals. We found that the blood alcohol levels of the people drinking the gassed champagne were higher for the first 20 minutes, suggesting that it got into the bloodstream a lot quicker.
OK, well, you have actually got some of these psychometric tests set up today. And now I had a go on 2 of them earlier this afternoon just to give an idea and get the score for what my ability is like without alcohol. And now, so I'm just going to finish off this champagne and then we're going to have a go on the tests and see if it's impaired my ability at all.
Yeah, an excellent idea.
OK, well, we actually have 2 of those psychometric tests. What am I supposed to be doing here again?
Well, the idea is to keep the centre of the cross on top of the ball as the ball moves randomly from side to side across the screen. The other part of the test is that you have to watch out for yellow balls, which will appear in the corners every now and then. And as soon as you see one of those, you have to click the button on your mouse.
OK, so I'm just having a go on this test again now and trying to follow this grey ball that's moving around with my green cross. So that one's finished. You've got both of my scores up here, and is there a difference between before and after I drank this champagne?
Well, there are differences. In your tracking, you've actually got better, but that, of course, is a practice effect. And when we did our study, we made the volunteers do it half a dozen times before they started to get rid of that as far as possible. But the more important component of the test is your ability to react to peripheral stimuli, the yellow balls, and your time there is actually longer.
Now, we've also got this second test set up, which is going to test my movement. So I'm just going to start this now, but can you just remind me again what the rules are?
This tests reaction times in 2 parts. There is a semicircle of lights which come on, and you have to move your finger as quickly as possible from a resting point to turn those lights off. So it has 2 components. One is how quickly you lift your finger up to say, oh, I've seen the light, and the other is how quickly you can get your finger over to put the light out.
OK, so that's finished now and all the lights have come on, so I think I'm meant to stop. How did I do here, Fran?
Well, you didn't do particularly well. Your reaction time to the lights was nearly 100 milliseconds slower. Your score at baseline was 362, and after you'd had your drink, it was 452 milliseconds. 100 milliseconds might not sound very much, but if you're driving a car, it's extra time it takes before you put your feet on the brake, and you could have gone quite a few metres down the road in addition to your normal brake time.
So I guess the key question now really is why this happened. Why does the presence of bubbles in alcohol make it affect our brains quicker?
Well, in order to affect the brain, it's necessary for the alcohol to get into the bloodstream. The way this happens is, obviously, you drink the alcohol which goes into your stomach. Not much of it's actually absorbed in the stomach. About 80% of it is absorbed when it carries on into the small intestine. The most likely explanation for champagne having a more intoxicating effect, therefore, is that it alters gastric emptying, the way that the alcohol or drink goes from the stomach to the intestine in some way. One possible mechanism is that it alters the way the pyloric valve opens or makes it open more frequently, because that's the part that allows the contents of the stomach to carry on its pathway into the intestines. Alternatively, it could be that the alcohol is absorbed as you're drinking it through the nose and through the mouth. That's much less likely. It's almost certainly something that happens once the alcohol gets into your stomach.
So, alcohol from fizzy wine actually gets into your bloodstream quicker, and it really does get you more drunk more quickly, if that's what you're after. That was Fran Ridout, who's now at St Bart's, explaining the science of insobriety to our very own Mira St-Thellingham.
Thank you very much, Helen. This is The Naked Scientist with Chris Smith, Helen Scales and Dave Ansell. It's our Christmas phone-in extravaganza. So if you've got a science question that you'd like us to answer for you, the email address for the programme is chris@thenakedscientist.com. And don't forget, if you've got a science fact that you think is totally gobsmackingly amazing, tell us it. We've heard from Lee E, and he says his number 1 is E equals MC squared.
Keeping you abreast of the world's best science. The Naked Scientists. For more information, look us up online at nakedscientists.com.
It's The Naked Scientists with Chris Smith, Helen Scales and Dave Ansell. Now, Helen, what are your 5 facts? We were asked by Ian Curzon for the top 5 facts that would wow out people down the pub.
Well, this is such a great question, and I have to say 5 is really hard. Thanks very much for that. But my first one, I think, is that in the dot of a 12-point letter I, there are more protons than there are seconds in 500,000 years. I thought that was quite mind-boggling.
It just goes to show the order of scale there, doesn't it?
Yeah,
exactly. How small we are right up to the macro,
Absolutely,
the universal scale.
In fact, that leads on to my second one, which I think is also great, which is if we made a scale model of the universe and we made planet Earth the size of a pea, the nearest star, Proxima Centauri, would be 16,000 kilometres away.
Which just goes to show how big the universe is.
Exactly
a
how
big
big the
place.
universe is.
Yeah,
I mean,
basically.
obviously, you could do that in any scale. But I just think that's fantastic.
And your number 3?
Just how big it is. Number 3 is biological. I've come back to the world of life and slightly more esoteric. But I love the fact that when caterpillars munch on plants, the plants themselves have evolved to emit a chemical, a smell that attracts other bugs that come and eat the caterpillars. Which it's such a crazy loop. I think that's awesome. And we think of plants sometimes as being a bit kind of boring and dull. They don't do anything. But my God, they're amazing. They're brilliant. So there you go. I think that's wonderful. My fourth fact is if you were to take Mount Everest and plonk it in the deepest part of the ocean, it wouldn't stick out of the surface. And in fact, you'd have to dive down over 2 kilometres to actually reach the top of Mount Everest. So, the oceans really are awesome. I know that. We know that. That fact, I think, tells it all. And my final fact is, there's all sorts of lovely statistics associated with blue whales, but I think maybe the nicest one, they're the biggest hearts in the world. Their hearts weigh 0.5 ton, and that's about the same weight as a mini car, which I just think is fantastic.
It's also the same size as a Volkswagen Beetle, I think, isn't it? You could almost drive a car down the biggest blood vessel in some way.
I think you can crawl down them. Yeah, you certainly could crawl down them yourself. So
drive
they
a
are
small
awesome.
car. Drive my daughter's toy car.
A little car, but no, they are such great creatures. I think all the facts about blue whales are brilliant.
Now, in this week's Kitchen Science, Ben and I looked at the ultimate lazy scientist solution to putting candles out on the other side of the room without even having to get up. But first, which freezes quicker, warm water or cold water?
Hello and welcome to Kitchen Science. This week, we're attempting to explore why warm water might freeze quicker than cold water. Now, I have spent days putting different combinations of warm water in a large cup and warm water in a small cup and different size ice cubes. And for me, the cold water always freezes quicker. Dave, you're the kitchen science guru. You must have found something different, yeah?
Afraid not. I again spent a couple of days freezing lots of different things. I tried deionized water, I tried Cambridge water, I tried boiled water, warm water, cold water. And as far as I can tell, cold water freezes quicker than hot water.
But Chris said last week that this week's Kitchen Science would be finding out why warm water should freeze quicker than cold water. It sounds illogical, but I understand there are some situations where it does actually work.
Well, I have heard from some quite reputable sources that you can get it to work, but I'm afraid I can't. So instead, we're going to do a different Kitchen Science. Now, I don't know whether you've ever had this problem, Ben. If you've been sitting at a table and there's a candle at the other end of the table and you can't be bothered to go over to the candle to put it out, and you'd really like a way of being able to put out the candle remotely.
This sounds like a very typical Christmas situation where you've stuffed yourself so full of food that you just can't be bothered to get up and blow the candle out.
Yeah, that's pretty much it, yeah.
OK, so you have some kind of long-range candle blowing out technique for us, do you?
That's the plan, yeah. All you need for this experiment is a candle, obviously, a lemonade bottle, a big 2-litre lemonade bottle, and a little bit of tape.
So how are we going to set this up?
OK, well, to be honest, it would work with just the empty lemonade bottle, but it's very, very hard to aim. So we're going to make some sights on this lemonade bottle. If you look very closely at the lemonade bottle, you'll notice there's a line running along it where the two halves of the mould were pushed together. And what we want to do is use this and make it a bit more obvious by sticking a piece of tape at each end of this line. So you can line them up and use them as sights.
OK, so let's get some tape.
So we want to end up with a lump in the middle. So I've just stuck the middle of the tape to itself with leaving 2 sticky bits at the ends. I'm just going to stick that on the line. Now the sight isn't quite in the middle of the lemonade bottle, so you've always got to aim slightly high. So what I'm going to do is aim slightly above the top of the candle, try and hold the lemonade bottle quite securely, and then hit it in the middle with one hand, whilst holding the other hand on the other side so it doesn't wobble too much when I hit it. And it might take a couple of goes. We'll just see what happens.
Nothing's happening at all, Dave. You're just making a loud noise.
Yeah, it does take a bit of practice.
So you're about a metre away from the candle. Is it not easier to be a bit closer?
Yeah, the closer you are, the easier it is to aim, fundamentally. You can do it from up to 2 or 3 metres away, but the aiming is a right pain.
Well, obviously the aim is a problem, Dave, because you haven't managed to do it yet.
Give me a few tries and we'll see what happens.
OK, so once again, Dave's lining up the bottle and hitting the side. Oh, that time the candle flickered, but it certainly didn't go out, so he must be getting quite close. That time it really did flicker. Must be getting... Yay! So you were about a metre, just under a metre away, and all you did was hit the side of your bottle, and it clearly blew out that candle. How does that work?
OK, to show what's going on a bit better, what I'm going to do is fill a bottle with smoke and try and do the same thing.
OK, so you have another bottle. This one doesn't have sights on it. And in fact, that's got some water in the bottom. How's water going to help you put smoke in there, Dave?
I'm going to put in some dry ice, which is solid carbon dioxide. And if you put dry ice in water, as the carbon dioxide boils, it takes with it quite a lot of water vapour. When that meets the air, it tends to condense into droplets. Basically fill the bottle with a small cloud. OK, so we're filling the bottle with water vapour, and this should hopefully demonstrate things for us. You have a polystyrene tub full of pellets of dry ice, and as soon as you drop them in, they bubble like mad, don't they, Dave? Yeah, you've probably seen this in pop videos. It's the stuff they use to make smoke on the ground in pop videos. Could this also be what they have for mad scientists' violently bubbling drinks? Yeah, it's always the same thing. Well, I suppose that mad scientists' violent drinks seem to suit us some way, but we've put a handful in now, and it's pouring out at the top. That is totally opaque now. It's just full of vapour. Yeah, that's what I was hoping to achieve. Now, if I squeeze the bottle more gently than I was before... Well, we're getting little puffs of this water vapour out of the top. If you look very closely, sometimes you can see little rings coming upwards quite fast. So it's really like you're blowing smoke rings using this bottle? Yeah, that's exactly what I'm doing. OK, so if I squeeze the bottle, that squeezes a bit of fast-moving air up out of the neck, and this meets the slow, stationary air from outside the bottle. Now, if you've ever watched water in a stream, when you get fast-moving water meeting slow-moving water, you get an eddy. There's a little swirl of water. Yes, you get little spirals all along the place where the two meet. Yeah, that's right. Now, the fast-moving air is meeting slow-moving air, but all the way around a ring. So you get a ring of eddy or a ring of a vortex. It's called a ring vortex. So rather than a sort of two-dimensional eddy where it looks like it's going in a little circle, this works all the way round the neck of the bottle, and you get a donut shape, a smoke ring. Yeah, so you get a smoke ring. And the really neat thing about smoke rings or ring vortices is that if you imagine the eddy going around it, if you imagine the eddy on the right-hand side, that's going to be blowing the left-hand side of the ring upwards. If you imagine the eddy on the left-hand side, that's going to be blowing the right-hand side of the ring upwards. So the whole thing gets blown by its own wind forwards and up and away. So it will travel a long way. So it sort of propagates itself by nature of its very shape, really. So what's this got to do with blowing out a candle over a long distance? Well, basically, when you hit the bottle really hard, you create a very fast-moving smoke ring with no smoke in it, so a ring vortex, which will travel across the room until it hits a candle, and there's enough wind in it to blow the candle out. And this is why you have to aim so carefully, because it's a relatively small ring that you're firing out. It's not like you're just going and pushing lots and lots of air past. Yes, you're right. It's a little disturbance which will move through the air several metres. Fantastic. So there you go. If you're at home with a candle on the table and you just can't be bothered to get up, grab yourself a plastic bottle, make some sights on it, and then spend a good 10 or 15 minutes working out exactly how to aim it to blow out the candle from the other side of the room. That's it for Kitchen Science this week. We wish you a very Merry Christmas, and we'll be back with more next year. Thanks, Ben, and it was a very long-winded way to avoid getting up, I'm sorry. We'll be back in 2009 with a fresh batch of Kitchen Science, but if you want to do a science experiment before then, we've got loads of Kitchen Science experiments to do on our website at www.thenakedscientist.com/kitchenscience, all one word.
Thank you, Dave. If you've got some science facts for us, of course, we're asking for your top science facts. Send them in. Chris at thenakedscientist.com. We've heard from Kevin, who's on the A12. He has 2 top science facts, he tells us. He says a picosecond is to a second what a second is to 30,000 years, which puts that in perspective. He also points out, and this is an amazing fact, the moon is 400 times smaller than the sun, but the sun is 400 times further away, so we get a perfect eclipse. What a fantastic fact.
What are your facts, Chris? We want to know what really makes your brain go wow.
Well, I was thinking about this earlier today, and I wrote at the top of my list that the human heart will beat about 40 million times every year of your life. And if you work out the weight of blood that it pumps around your body, it's lifting about 7 tons of blood a day. And if you tot that up over a lifetime, that's about 2 very large aircraft carriers that your heart has lifted in terms of the weight of blood it's pumped in a lifetime, which is pretty fantastic when you think of the work that nature's polymers are doing. Evolution has given us a heart that can do something, so much work for so long and work so faultlessly in the vast majority of people.
We should look after our hearts if we're asking it to do all that work as well.
My second fact was the age of the universe, because I just find it mind-boggling that we can say the universe we live in is about 13.7 billion years old. And we can date that, and we know that that was the moment when our universe popped into existence, begging the question, well, what went before? What's this universe which is expanding into? Are there other universes? And I just find the whole thing a bit spine-tingling, and that's why I like that fact. My number 3 was that scientists reckon, conservatively, there are about 10 to the 22 stars in the known universe. That means there are 10 to the 22 stars, possibly a bit like our sun, many of them a bit different, of course, but that means the prospect of finding another system like the system we're in, with our Earth at the right distance from the sun, with liquid water and the right recipe for life, it doesn't seem so unlikely when you think there are 1 followed by 22 zeros after it. Opportunities for that to possibly happen. That's a pretty good odds.
That's really cool, and it kind of ties into my fact as well, the one about how far away the first star would be. Because if that's just the first one, it's 16,000 kilometres. If the Earth was the size of a pea, how on earth are we ever to get our heads around how far away all the other ones are? That's awesome.
Now, my fourth fact is something that I've always had tremendous respect for, which is that I share, and everyone in this room shares, about 60% of your genes with a banana. Not because we're particularly vegetable prone, but because the genetic code, it doesn't matter whether you're E. coli or a human being, you have exactly the same genetic code running in you. In other words, you can take a gene out of a jellyfish, put it into E. coli, and E. coli will glow green like the jellyfish did, because the genes that work in us work in bacteria, which shows we all came from, in evolution, a common ancestor somewhere. And my final fact is that, can you guess what the fastest living creature on Earth is?
Should be a cheetah, surely.
I want to say cheetah, but probably actually a whale or something. A dolphin.
Guinness Book of Records for the world's fastest creature is a bacterium. And it's Delovibrio, and it moves at 60 body lengths a second. And it does that.
But it's tiny though, isn't it?
Yes, but it's all relative, isn't it? Size is important. If you're bacterium, you wouldn't expect it to be able to compete with a cheetah, because cheetah's a little bit bigger. But 60 body lengths every second. I mean, if that was an aeroplane, it would be flying at incredibly fast speeds, which I find absolutely amazing. It does it with a propeller, with a little propeller called a flagellum, which is sort of nature's propellers, tiny proteins that whip along and force the bacterium along. They're actually predatory bacteria. They invade and eat other bacteria.
Sounds nasty. Can we harness that energy? I think bacteria energy, that would be great. What do you reckon?
I reckon. Thanks, Helen. It's The Naked Scientists with Chris Smith, Dave Ansell and Helen Scales. It's our Science Christmas phone-in extravaganza. If you have a science question for us, the email address is chris@thenakedscientist.com. On the way, this week's question of the week, when we'll find out whether you should scoff all your Christmas goodies in one go on one day, or whether you should pace yourself and maybe enjoy them over the subsequent 2 or 3 weeks.
Distilling the best science. The Naked Scientists. For more information, look us up online at nakedscientists.com.
You're listening to Naked Scientists, and now it's time to invite the lovely as ever Diana O'Carroll back into the studio for our question of the week. Hello, Diana.
Hello, Helen. Well, this week I've been scoffing down literally mountains of chocolate in the name of science for this question.
Hi, I'm Marie from Harrogate in North Yorkshire. My question is, this Christmas, when I get loads and loads and loads of chocolate for Christmas, will it be better for me to eat it all at once, or will it be better for me to eat maybe about 5 or so a day? Not that I'd plan to, of course.
So, to have a Merry Christmas binge or stretch it out over the holiday?
My name is Linda Morgan. I'm a professor of nutritional endocrinology at Surrey University. Okay, so better to eat your chocolates all in one go or a few at a time? Well, the short answer is that it doesn't actually make any difference. The extra calories will be the same in each situation. The only effective way to prevent weight gain is to not eat the extra chocolate in the first place, I'm afraid. Evolutionarily, we evolved for feast and famine, and we needed to build up all the body fat that we should have got in the feast times to see us through the famines. However, if you do eat all your chocolates in one go and you felt queasy afterwards, then you're probably less likely to build up a sort of chocolate habit that lasts well into the new year. On the other hand, if you eat a few chocolates each day, you may well end up with a habit that is quite hard to break in the new year. So if you have to eat chocolates, have them all in one go and make yourself sick.
So it turns out you can't fool your intestines into missing a few calories by overloading them. What a shame. Well, next time on Question of the Week, we'll be looking at things from outer space.
Hello, my name is John Wilson. I live in Zeist in the Netherlands, near Utrecht. And my question this week is related to something that I heard previously on The Naked Scientist, and was to do with lots of rubbish falling to Earth from outer space. And I wondered whether they'd found any life in the rubbish that falls to Earth.
So, are there any fossils floating around in space? Let us know what you think by emailing chris@thenakedscientist.com or by writing it on our forum. That's at thenakedscientist.com/forum. And as a special Christmas treat, we've uploaded a whole year's worth of Question of the Week to iTunes, so you can download those now at any time.
Thank you very much, Diana, and thank you for a wonderful year of Question of the Week. That's Diana O'Carroll, and she'll be back in the new year with more fantastic questions.
Laying the facts bare. I say. The Naked Scientists.
This is The Naked Scientists with Chris Smith, Helen Scales and Dave Ansell. John's on the line. He's got a question. Hi, John.
Hello, Chris.
What do you want to ask Dave?
Yes, it's just a question about light. I just wondered whether it ever decays. You know, you hear about light years in space and light travelling hundreds and hundreds of light years, or thousands or millions of light years.
So does the light go on forever, or does it? So does the light go on forever, or does it eventually peter out?
Does it go on forever? Is it the frequency? Can we ever amplify the frequency of light so we can see very much detail on what we can see, or is it just optically? We use telescopes, don't we? We've got the Hubble Space Telescope.
Sure. OK, well, let's find out, John. I've also got a question to add to that, Dave, which is an email from Hunter Wilson, who says, is there a limit to how bright light can be?
OK, these two are actually slightly related. Basically, light will carry on going for an awful long time. As far as the photons which were created at the end of the Big Bang, that's when, it started off with during the Big Bang, there was a big soup of protons and electrons, and as soon as the electrons kind of got trapped by the nuclei of the atoms, and the universe went transparent. There have been photons which have been travelling since then, which is about 13.7 billion years ago. They reach us as part of the cosmic microwave background radiation, and they've carried on going. What they have done is, because the universe is expanding, one way of thinking about it is that they've been stretched, so their wavelength has got longer. They've moved further red. They've become more and more red. It's called redshift, which is the reason why the sky is black. Because if there was none of this effect, then you'd see the effect of the Big Bang. It's incredibly bright, in fact, gamma rays being emitted all around us, and the sky would be bright white, in fact, bright X-ray, really. But because the universe has expanded so much, these photons have been stretched, so they're actually in the microwave region. So the photons will carry on going forever, but they can change their wavelength. Is there a limit to how bright light can be? The only one which I have found possibly is that if you get to incredibly bright lights, photons will actually start to scatter off each other. People have suggested that in order to be able to just see this effect, you'd need an exawatt laser. That's a billion watts of energy, so a billion nuclear power stations being funneled into probably something the size of a cubic millimetre. And then you might see photons, instead of just going straight past each other, bouncing off each other, at which point then they'll start bouncing off each other and you won't actually be able to get much brighter. You probably get a lot brighter than that, but there would be a limit somewhere beyond that.
Now, Mike Kant, who goes by the name Tarquin of Sailing, says, how far back can we observe in the universe, both in terms of distance and time?
The limit is this point at which the universe became transparent, which is about 400,000 years after the Big Bang, because before that the universe got free electrons in it, and electrons interact with light very strongly. So the light just hit an electron very soon, and it essentially stopped. So that's the limit that we can see back.
And Ali and Steve, sorry to pound you with these, Dave, but you're talking about light. We might as well carry on. Ali and Steve listening in Australia, and they say, is there an antimatter equivalent to light? Because we have matter and antimatter. You put the two together, they cancel out. Does the same thing apply to light?
In some senses it does. There is an antimatter equivalent to a photon. It's another photon. If you have two photons with exactly the opposite phase, they can cancel each other out. And as far as we know, that is all you need. The photon is its own antiparticle.
Thank you, Dave. Helen, quick question here for you. This is from Nigel Edmonds, and he says, what do earwigs eat?
Earwigs, fortunately, don't eat our brains. I think that was a bit of a wives' tale, isn't it? They crawl in your ear and eat your brains. And they eat all sorts of stuff. They can eat plants. They tend to kind of dig out sort of dead things. They're really omnivores, essentially. So plants, flowers, other animals, other insects. But I think that we can basically be rest assured that they don't eat our brains.
Which is good news.
Good news.
Dave, this is your opportunity to tell us what your 5 fabulous facts are. We've heard from everyone else. What are your 5 facts that are going to wow us out?
Well, quite a lot of my facts have been quite related to the show so far. My first one was that light travels at 299,792 kilometres every second. So stuff which is hitting your eye is going ridiculously fast, which I think is quite incredible. The other one, again, related to the show, is that light from the Andromeda Galaxy, which you can see with your naked eye, has been travelling for 2.5 million years just to get to your eye. Third one was that some of the static your TV picks up, which is actually some of it is the cosmic microwave background radiation, which I was talking about earlier, has been travelling since 400,000 years after the Big Bang, so for 13.7 billion years without hitting anything, and then it hits your radio. And then into something a bit more down to earth. A typical hurricane uses the same amount of energy as exploding 8 billion tonnes of TNT.
So that's pretty powerful.
Which I think is quite incredible, just the sheer power of nature. And then just for what humans can do, the fact that a modern modern processor has got 580 million transistors on them, some of them 2 billion. But 35 years ago, the first processor only had 2,500. And I just think the advance is incredible.
My first computer, not that long ago, 20 years ago, had 32k of RAM. Isn't that amazing? You've got computers with 32 gigs of RAM. Now, Helen, I've got a question here for you. This is very, very brief from Mark Stipetic, who says, why are flies so difficult to swat? Do they just have very fast reactions, or is there some other factor at work?
Well, there's actually a couple of different things. I mean, you're quite right. Flies are really hard to swat. I think maybe if you cool them down, that might be a better way of actually catching them, but I've never tried that.
Not very practical, though.
Not very practical.
Cool your entire house down
exactly,
just so you can catch the
squirt them with a jet of cold. No, that doesn't work. But anyway, it's partly to do with their eyes. They've got incredible eyes, not just a single eye like we have, but they have multifaceted compound eyes, so they're collecting light from all different parts of the room, so they can really see all around them. So they can definitely see you coming. But another reason, which was actually just come up this year in a study from Michael Dickinson of the California Institute of Technology, and they discovered using incredibly high-speed video cameras that, in fact, just before they take off, flies actually adjust their position so that they actually jump in the right way. So they can work out what's coming at them and from what direction. So they can actually hear you kind of approaching with your swatter through as it swishes through the air.
Hear or see as well?
Presumably they can see as well, yes, absolutely. And by making that calculation of what's coming at them, they adjust their position of their legs so that when they do decide to take off, if they do decide, sometimes they actually change their mind and they actually change position about to get ready to go, and then they might suddenly decide, oh, actually, I'm not being hit after all, so they don't go. But they do kind of manoeuvre themselves. So they're ready to go in the right direction when they do take off, which is just incredible. And it's incredibly quick. This is the only reason we've only got this now is because we've now got such high-speed cameras to actually track these movements and to show them positioning themselves in space so that they actually, take off and fly off in a direction that you weren't expecting, maybe. And it's gone before you get a chance to aim again. So they really are awesome creatures. And we may not like them, but they are really quite incredible.
Yeah, fly spray, DDT. That's the answer.
Nasty stuff.
Thanks, Helen. Right, well, that's it for The Naked Scientist for 2008. And I have to say a very big thank you to our absolutely superb production team here at this end. That's Ben Vousler, Dave Ansell, Mira Senthilingam and Diana O'Carroll. We're back in 2009 with more Naked Scientist shenanigans, but we do have a couple of Christmas presents for you to enjoy while we're away. So if you check for an update on Christmas Day, you'll be introduced to our first foray into video podcasting with Science from the Sporran, in which the inimitable Dr. Ernest Otherford, you'll work it out, takes you on a kitchen science experiment an adventure with a difference. Also next week we'll have an episode from a brand new podcast we're launching, which is called Naked Archaeology. And in this episode, Diana O'Carroll will be exploring, amongst other things, some mysterious mummified fetuses that were found alongside the body of King Tutankhamun in his pyramid. So, I hope you enjoy all of that. In the meantime, we hope you have a terrific Christmas and New Year. Thank you very much for listening to us this year. We really value your support, and please do keep sending in the great questions. That's to chris@thenakedscientist.com. Have a great Christmas, take care, and goodbye.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.